things it is. These are 3 landmarks in the environment. These are the observations. So the robot could say, okay, either this guy goes here or goes, so corresponds to this landmark or to this landmark, and the same here. And kind of, if this one should be this landmark, it's quite likely that this one will be this landmark. But in theory, you have all possible assignments of observations to landmarks. And the problem is there's a large number of possible data associations, and the number of possible data associations depends on the pose of the robot. So if I would know that the robot was sitting, let's say, over here, a little bit rotated to the right, it's quite likely that the kind of red association would be the most likely, or at least the most likely one. If the robot was sitting a little bit more to the left, rotated to the left, the blue one is likely to be the correct one. So the pose of the robot influences the data association. And this is now a great advantage for the FastLAM algorithm. And the reason is that I can do my data association on a per particle basis. Every particle can make a different data association. And if a particle does good data associations, it's more likely to survive the resampling steps compared to a particle which does bad data associations. So the big advantage is now, if the robot is sitting over here and observes 3 landmarks, it's quite likely that this is the data association that it did. If the particle sits down here, it's quite likely that this is the data association. And particles here in the middle would get a lower weight because they don't fit to any of those constellations very well. And this is one of those situations where you quickly get a multimodal belief. So it says the robot went either here or here because both observations fit very well with the pattern of landmarks that I see. So I will end up in multimodal beliefs, so not this kind of nice banana shape or Gaussian distributions as seen over here. And this is one of the advantages of the particle filter, that I can do the data association on a per particle basis. Another example is this example over here. So the robot sits over here. These are 2 landmarks in my map, and that's the observation that the robot gets. And the red or the brown landmark. What I can do now, I can just compute the Mahalanobis distance of the expected observation with respect to those 2 landmarks over here. And this may result in the case that, okay, with probability 0.3, it's the red one. With probability 0.7, it's the brown one. What should I do? The standard approach is, okay, just take the most likely one. But what I can do now here in this situation, I can actually sample it. Just say, okay, I don't know which one it is. I just draw with one landmark with a probability that is actually given by the individual probabilities. So if I would sample here 10 times, 7 times I would draw the brown data association, 3 times I would draw the red data association. And if I have a large number of samples, I can just sample those data associations. So some samples will draw the right data association, some samples will draw the wrong data association. As a result, they will come up with different maps, and at least the hope is that in the long run, those which did the right data association survive, and those which did the wrong data association die out. Of course, this process may take some time. I need to have a sufficient number of samples to cover all the different possibilities, but the particle filter has these possibilities. So, yeah, there are, as I said, multiple options. One is pick the most probable match. That's what the standard EKF would do. But again, I can pick a random data association and weight it with the probability that is the right or wrong data association. Exactly what I explained before. And what I typically have, I have a threshold. If there's no landmark which has a high likelihood of being a association, I assume it to be a new one. But again, that's an assumption. So the nice thing in here is that this is a very easy strategy. It's very simple to implement, but has very nice properties. And this is one of the advantages of the for FastLAM compared to EKF, that I can do very simple but effective data associations. And the reason for this is that I don't have a parametric form which describes the uncertainty of the robot. I have this sampled belief. In this sampled belief, you can say, okay, for this sample, this is the right data association. For this sample, this is the right data association. And this sampled representation makes it very, very easy for me to make this advanced data association, having multiple data association possibilities in my belief. This is something which naturally evolves from FastLAM, and the advantage here is the sampled belief compared to a whatever Gaussian distribution or other parametric form that I have. And this is kind of one situation where the sampled belief is really, really advantageous and offers me a nice possibility to do that. Okay, let's see how this this FastLAM actually compares to this Victoria Park data set. You have seen that. There's just one example where you can then use the GPS information to analyze the error. Again, you see it's not a perfect estimate, but it's typically better than what the EKF provides. Also a small video where you can again see that. Again, it's a video of Mike, provided by Mike. So you can see the robot driving around here. These red dots are the observations, also the uncertainty of the observations in the model. Blue is, in this case, the odometry, so it's not the ground truth information. So a little bit inconsistent in the coloring for the video. Sorry for that. And so the red trajectory here is the trajectory of the FastLAM algorithm. At least you can see that using odometry would give you a pretty inconsistent estimate. At least something you should see from this plot over here. Okay, that goes on for quite a while. One thing one should analyze is which impact does the sample size have on this algorithm. Because obviously, if you just take, let's say, a single sample, you're quite likely to perform poorly. How does it change with 10 samples? How does it change with 100 samples? So typically, the higher the number of samples, the better is your estimate. And what you can see over here is if everything is perfect, so this example, this was a simulated data set, everything was perfectly Gaussian, then it's just that the performance of the EKF in terms of quality of the results is actually pretty good. And this also assumes that you have a low motion noise, or at least you have a roughly linear function for your motion noise. If you now increase the motion noise of this algorithm, the results look substantially different. Then the performance of the EKF dramatically decreases because the nonlinearity in the motion kind of kicks in, combined with a large uncertainty gives you bad estimates of the pose estimate. And so the error here dramatically increases, while it basically not noticeably affects the FastLAM algorithm. So it's an interesting algorithm which has some very nice properties. So try to get rid of the EKF to model the joint posterior. Just says, okay, I'll split that up with one part, especially the one which also the motion is represented by a linear function. I use a particle-based representation, so I can multimodal belief where the robot is. And then given this multimodal sampled belief, I compute a distribution over maps where I said every particle has its own map. And this way I can also take into account different data associations on a per particle basis, which is really an advantage if you don't have a good technique to get, let's say, a good feature descriptor, which always gives you very good data associations. As I said, it models the robot's path by sampling, so by samples. It computes the map given the path, and we can do a per particle based data association. And as a result of that, and this is the reason why the data association is simpler in this case, is that you can you don't have a distribution. So for every data association decision that you do, you don't have a distribution about the robot's pose, but you have a concrete instance. The robot was here. That was the sampled belief, and this makes it easier. Of course, you have to do n data associations for every particle, but it's much easier to do n simple data associations than one complex one where you have to reason or integrate over possible data associations given the uncertainty of the vehicle itself. Okay, the next thing I would like to do is look into the computational complexity of that algorithm. So let's have a look and analyze this algorithm. What do you think is the computational complexity of standard FastLAM? What about integrating the odometry information? How complex is that?